Let's take a look at number 1. We need to draw a free body diagram here. We are given the weight of the girl, and we are also given the applied force, so let's fill that in. The normal force is going to be the same as the applied force, so we need to figure out the force of friction here. We know that the sum of the forces equal mass times acceleration. Well, the sum of the forces are the positive force minus the negative force. In this case, we're talking about the x direction, so the positive force would be 13. The negative force would be the force of friction. And all that equals mass times acceleration, which turns out to be 0. Because, if you look at the problem, it says that she's pulling the sled at constant speed. Constant speed means 0 acceleration. So the entire right side of the equation is going to go to 0. What that means is that 13 equals the force of friction. Let's think about our formula for the force of friction. We know that equals mu times the normal force. We do not know what mu is, but we do know what the normal force is. So we can plug that in, divide both sides by 52, and we can solve for mu. Anytime you're solving for mu, you need to make sure that your number is between 0 and 1. And mu is unitless. In this problem, we are given the applied force. We also know how heavy the sofa is. So if we know how heavy it is, we can multiply the mass by 9.8 to figure out the force of gravity. And then once we do that, we also know the normal force, because the normal force is equal to the force of gravity. When you're getting something to start moving for the very first time after it's been sitting still, at that moment that you get it to move, what that means is that you have equaled the force of static friction. So at that moment that your box begins to move, your applied force is equal to your force of friction. So we can say that our applied force of 102 newtons is also the same value as the force of friction. So we can then plug 102 into our formula for friction and solve for mu. Again, we're making sure that mu is between 0 and 1, and mu does not have any units. It is simply a coefficient. In problem number 3, we have an applied force. We're dragging a box of books. We also have a force of friction. We know what the weight of the box is, so that's going to be the same as the normal force. We also know what the coefficient of friction is. So let's plug that into our formula for the force of friction so that we can get the actual value of the force. Now that we know that, we can figure out the applied force. In order to get something to start moving, you have to equal the force of friction. At the moment that that box begins to move, the applied force is equal to the force of friction. So, if you know the force of friction, then you know the applied force, because they're going to have the same value at that moment. In number 4, we have a similar sled, but we have a little bit of a different weight, because this time we're taking the weight of the sled and adding it to the weight of a person for a total of 702 newtons, so that's also going to be the new normal force. Let's take a look at our equation for the force of friction. We know what mu is, it's provided in the problem. We know what the normal force is, so we can find the force of friction. So, we're pulling this thing at constant speed. We need to think about what that means. If you're pulling a sled at constant speed, that means 0 acceleration. So the forces are going to be equal on both sides. The force of friction is going to equal the applied force. Well, we know the force of friction, 84.2 newtons, so we also know the applied force, 84.2 newtons. In question number 5, we're talking about the difference between different coefficients of kinetic friction. We're given the force of friction when the coefficient of friction is 0.58. So we can divide the force by mu to find the normal force. Once we have the normal force, we can figure out what the force of friction would be with a different mu, because the formula for the force of friction is mu times the normal force. So given the new mu, and knowing what the normal force is, we can plug in to solve the new force of friction. In question number 6, we have a sliding block that's slowing down. It's really important in these situations to remember that there's no applied force. There once upon a time, to get that block moving, but at the moment that it's just sliding across the ground and slowing down, the only force in the x direction is the force of friction. So we can set this into Newton's second law. The force of friction is going to be equal to the mass, which is given, times the acceleration, which is given. So we can find the force of friction. Let's plug that into our equation for the force of friction. We're going to need the normal force. We can figure that out. You just take the mass and multiply it by gravity, 9.8. Now that we know the normal force, we can put some numbers into this thing. You can divide both sides by the normal force, 13.72, and solve for mu. We need to make sure that mu is between 0 and 1, which it is. Number 7, we're pushing a bookcase across the room. We're given the weight of the bookcase. We're given the mass. So we can figure out the weight by multiplying by the acceleration of gravity. That's also going to be the same as the normal force. The applied force is also given in this problem. Let's take a look at Newton's second law. The sum of the forces equal mass times acceleration. In this case, the mass is given and the acceleration is also given. The only unknown right now is the force of friction. We can solve for that. Now that we know the force of friction, let's plug that into our equation for the force of friction, mu times the normal force. We know the force of friction. We do not know mu, but we do know the normal force. So we can divide both sides by the normal force, and we can solve for mu. Make sure that it's a number between 0 and 1. Question number 8, we have a shuffleboard disc that's sliding across the ground and slowing down. It's very important to recognize here that there is no applied force. There was once upon a time when you pushed it, but right now it's just sliding across the ground and slowing down. So the only force acting on it in the x direction is friction. Let's take a look at Newton's second law. The sum of the forces equal mass times acceleration. So really just friction equals mass times acceleration. Well, that doesn't do much good. We have too many unknown variables. But take a look at what I did there. I expanded the force of friction into mu mg. Remember that the force of friction is equal to mu times the normal force, and the normal force is equal to mass times g. So, we can say that the force of friction is equal to mu times m times g. The right side of the equation doesn't change. That's still ma. But look what happens. We can cancel out the m's. So now the mass is negligible. Now we simply have mu times g equals acceleration. So now we're in business. We know what mu is, and we know what g is, so we can find the acceleration of the puck. Once we find the acceleration, it simply becomes a kinematics problem. We know the velocity initial, it's given in the problem. When it comes to rest, the velocity final is going to be 0, and we've already found the acceleration, so we can plug this into our VF squared formula and solve for the distance. In question number 9, we have Mr. Warner driving home at night. He's slamming on his brakes. That means that there's no applied force in the positive direction. We only have the force of friction in the negative direction. Let's find the force of gravity by taking the mass of the car and multiplying it by 9.8. That's also going to be the same as the normal force. We can find the force of friction because we know the coefficient of friction, it's provided in the problem, and we know the normal force. Once we have the force of friction, we can set up Newton's second law. The sum of the forces in the x direction equal mass times acceleration. We know the mass, that's given. We don't know the acceleration, but we can find that by dividing both sides by 2400. It's going to be a negative number, but that makes sense because we're slowing down. So now, let's set up our kinematics equation. We have the velocity initial, that's given. The velocity final is 0 because we're coming to rest. The acceleration we've just found, don't forget it's negative. And we want to know, is the distance 60, or is it greater, or is it less? So let's solve for d and find out. We can use the VF squared formula. We have everything that we need. It turns out your displacement is 65.8, which is bigger than the 60 that the tree branch is away. So it turns out we're going to hit the tree. I hope that this was helpful.